So hi everyone, welcome to my YouTube channel. So here I am going to explain you about the experiment on half-life of K40. So let us start. So half-life of K40. Aim of this experiment is to determine the half-life of K40 and specific beta activity of K40. So what is half-life? Half-life is the time taken for radioactivity of a specified isotope to fall off its radioactivity to half its original value. So here we have selected K40, that is potassium 40. Atomic number is 19 and mass number is nearly 40. So the potassium half-life is around 1.28 into 10 to the power 9 years for when it decay by emitting beta rays. So when it emits positron and decay, its half-life is going to be 1.19 into 10 to the power 10 years. Okay, so we have to find this experimentally. So here the apparatus we require here are GM counter, GM tube, beta source, KCl powder. So potassium chloride we have to select, which contains this K40, aluminium container and fractional weight box and lead shield. So here you can see this is the GM counter, GM tube or detector, this is source holder, and here are the aluminium containers which contain KCl, okay, KCl powder. So here we have to find out the half-life of K40. So here this is the beta source, that is bismuth, okay. So first what we have to do here for this experiment, we have to find out the operating voltage, okay. Already I have explained this in the previous video. So before that you should understand the theory for specific beta activity, okay. Just you can read about the theory. Then here just what is half-life you should understand. So here as I defined, the time taken by the half number of atom substance to decay completely is called half-life. So here is the equation for half-life, 0.69 divided by lambda. Lambda is what? Decay constant. So here the procedure, just I will explain you how to take the readings. This is what source holder. Just you can see the diagram. So nature of graph, here three nature of graphs we have. One is for operating voltage and another one is for weight of KCl versus N, and another weight of KCl versus log N. So first observations you should note down for the operating voltage, that is GM counter used, end window GM counter, and source used beta source, and the paralysis time we should keep it off for operating voltage, and then preset time you should keep 30 seconds. So just you can measure the applied voltage versus number of counts, and then you can plot the graph. So operating voltage for this experiment they got about 440 here, okay. It may vary, but for their present work or the readings they got, for that they got operating voltage 440. So already in the previous video I have explained how to take the operating voltage. Just go to that video. After that you can plot the applied voltage versus number of counts. So here is the nature of this is the graph for operating voltage. Just you can take V1 plus V2 by 2, you will get the this plateau, that is you are going to get V0 operating voltage. Next, in the second part, you have to determine the half-life of K40. So for that you should write down your observation: GM counter, end window GM counter, inner radius of the container, and source. Here is the container which contains KCl powder. You have to measure the diameter and you can measure the radius. Then source used, beta source, as I said, bismuth. Okay, then paralysis time off. So here you should go to the program key. Already the operating voltage has been set using this knob 440. Okay, then here in this program key you can select paralysis time, that must be off. So here you can see it is off. Then distance between the source of the GM tube, distance between source and GM tube. So this is what source, 4.5 centimeter. This is 1 point. Here you can see this is the source holder. You can keep here the source at about 4.5 distance. You can measure using your normal scale the distance from the detector to the source. Okay, 4.5 centimeter. Then inner radius of the GM tube. So it is already measured. This is the GM tube. The inner radius they have measured here. It has been given 0.457 centimeter. Percentage of abundance of K in KCl. So here is the KCl powder. How much percentage of K is there in this KCl? So it is also fixed value, constant, 0.0188. The molecular weight of KCl. So the molecular weight also is going to be the fixed number, 74.56 gram per mole. Amount of K in 1 gram of KCl is, these values already, the fixed values, you just note down this, 0.5243 gram. Efficiency of GM counter, that is 0.98. And then Avogadro number, background counts you have to take here for 900 seconds. Okay, background count rate you can calculate after taking background counts for 900 seconds. And operating voltage we already found that 440, just write down. So background counts you can take it for 900 seconds. So without source you have to take background counts. So already I have explained how to take background counts. So 900 second means you are going to get high number of background count. So they got about 401 divided by 900. If you do background count rate, you will get. So the next here you have to plot the tabular column 2 here, weight of the container. So these are the containers. Okay, these are what, aluminum container. You can see. So here we have mentioned below the numbers 1 to 5. So here we have used 5 containers of different weight. So we have already measured using weighing machine. The first container weight is 2.01. So second, it is going to, we have selected in the increasing order. Just write down the weight of the container. You must weigh in the weighing machine. So we have weighed all these 5 containers. Okay, so we have written from 2.01 to 3.38, 5 containers. We have given the numbers here, 1, 2, 3, 4, 5. Then weight of container with KCl. So empty container you have to weigh without KCl. After weighing these containers, weight of the container without KCl, W1, weight of the container with KCl. So this is with KCl. So with KCl, if you measure for increasing order, all the 5 containers, 1 to 5. So we got for the first container 3.642 weight of the container with KCl, W2. Okay, write down similarly for up to 5th container, 4.87. Then weight of the KCl, how we can find out? W is equal to W2 minus W1. So weight of the KCl we can get here for containing in all the 5 containers. So weight of the KCl in first container is 1.632. So similarly you can calculate for other containers. So next what you have to do? So first what the observations we have written here, paralysis time of preset time must be 900 second, and voltage, operating voltage they got 440. Okay, then say store, we kept this source at 4.5 distance centimeter. Then I will take the first container here. Okay, so like that you have to keep above the source. Okay, then you can just store, already we said, so click on start for paralysis time 900 second. So 900 second means it will take about 15 minutes for one reading. So there are totally 5 containers containing KCl. So 15 minutes means it may take a lot of time, around 1 hour 15 minutes time it will take for 5 readings. So first reading I am taking for 900 second. So just like that you can repeat the procedure for the remaining containers 2, 3, 4, 5. Okay, how many counts you will get? It will stop after 900 second. Note down the counts here, it is still increasing. When it reach 900, just you can note down the counts. So here for first container containing KCl, they got number of counts, that is 573. So at this distance, and when we keep the KCl above this source, then this count rate is going to decrease. So for 900 second you are going to get the counts around 500 or 600. Okay, so number of counts for t in second you can write. So you can see it will take 15 minutes. So just I am showing you how to take the reading. So just repeat the same procedure. So it may take still 10-15 minutes. So that's why just understand the procedure. So 573. So for second container they got about 635. So like that you can note down the reading. Count here, corrected count per minute. Okay, count rate that is here corrected count per minute that you can get by capital N is equal to N star minus B by here that is rho omega. So corrected count per minute you can calculate using capital N is equal to N star minus B by P into omega. P is what here? Percentage of abundance of K in KCl, 0.0188. Then B background count, N star number of counts for T in second, omega weight of the KCl. After calculating this column for all the different weights, take ln N. Okay, So after the calculation of ln n, just go to the table 3. First here you have to take weight of the KCl in gram, that you can consider it as xi. So this column in the table 2. So table 3 you have to take the first column as weight of the KCl in gram, then ln n, this last column, okay, consider it as yi, then use the LSF method, okay, and do the calculation. So then after using LSF method and doing the calculation for all the parameters, just you can calculate here the slope and intercept. Before that, just you can see p value, pqrs values once you get from the LSF method from table 3, also y bar value, then go for the calculation for slope m using pqrs, then intercept, okay. After that, error in slope you can calculate using the formula given here, then error in intercept. So the calculation is more huge here, so just go for standard deviation. So all these parameters you can calculate using LSF method, that is slope, intercept, error in slope, error in intercept and standard deviation. Then geometric factor, if you read the theory, you are going to come across this formula geometric factor G, that is given by this formula. Here you require beta and gamma value. So these values you can get from the value of A and B, C. These values you already written in observation, that is A is what here, distance between source and GM tube, B inner radius of the GM tube, and the C is what here, all these values inner radius of the container. So A, B, C value required to calculate beta and gamma, okay. Then you can calculate G value using beta and gamma values, you will get around 0.4946. Then after this calculation, you can calculate from the graph ln n versus weight of KCl. And one more thing, you have to plot the graph from table 2 here, the graph of first graph, that is nature of graph already I have shown you. So n versus weight of KCl, okay. Then the another graph is ln n versus weight of KCl. So these two graphs you have to plot. So from here the calculation from graph ln n versus weight of KCl, if you plot, you will get the intercept, but here you can use the intercept from the LSF method as well, okay, 12.0261. So n naught is equal to ln n naught is equal to E. So n naught value you can find out. So specific beta activity, once you calculate n naught value, you can calculate using this formula specific beta activity. Here alpha, E and G. G value geometric parameter, that we have factor we have already calculated. So here E and alpha value also given in the observation, that is alpha is equal to amount of K in 1 gram of KCl, and M is molecular weight of KCl, here efficiency of GM counter 0.98. Using these values you can calculate the specific beta activity. M value you can use afterwards. Here for radioactivity you require M, N naught, P, Avogadro number, E and G. Already all these values you know. So source specific beta activity calculation, and here radioactive beta decay constant you can calculate. Lambda you will get around 2.27 into 10 to the power 13. half life of K40. So half life equation is what? 0.693 divided by lambda. Lambda you can substitute here and you will get the half life, that is 3.05 into 10 to the power 12 years. Okay. Error in n naught. So you can calculate using n naught into sigma c. Okay, error in slope, and then error in specific beta activity, delta s is equal to sigma c into s. Then error in beta decay. So error you can find out using these formulas. Then error in half life, okay, using delta lambda divided by lambda decay constant. So you can calculate here error in half life. So this is about error analysis. Then at the end you can write the result here. Geometric factor G, specific beta activity S plus error in beta activity, then half life of K40 plus or minus error in half life, specific standard half life of K40, actually 1.29, as I said in the beginning, 10 to the power 9 into 9 years, but they got around this value. So radioactive decay constant lambda plus or minus delta lambda. So this is all about the half life of K40.